So good afternoon, all of you.
Good afternoon, sir.
Good afternoon, sir.
Yeah.
Good afternoon, sir.
So welcome to this discussion hour. So I open the house for any queries, for any doubts that you may have. Yeah. Yes, any doubts you have? Don't have any doubts?
Sir, can we explain the theorem that there is a sequence of priors pi m, that theorem?
Regarding admissibility?
Yes, sir.
Okay. So let me first share the screen. So Bayes rule, you know, right? Bayes. So what happens in the Bayesian setup is this parameter. So let me just go briefly explain. So this is the model which you can see the screen, right? All of you?
Yes, sir.
So this is the probability model which is under your consideration. So suppose functional form of f is known. The only unknown quantity is theta. So sometimes what may happen is you might have a prior information about theta in terms of a probability distribution. So that means theta itself is a random variable, right? For example, if you are interested in estimating the height of males in India, from past generations, you might have some informations about the height of males in India. So that prior information has been quantified in terms of a probability distribution. So this theta itself becomes a random variable. So now when you have taken a data, you have two sources of information. One source of information is this prior distribution theta, and another source of information is your data, x. So what you do is, once you have observed the data, you would like to update your prior information, right? So that means distribution of theta given x, you would like to find it out, right? And that is called a posterior distribution, right? And what is the Bayes risk? Bayes risk is the average risk with respect to the prior distribution which you have, right? So Bayes estimator is the one which minimizes this Bayes risk. And then you have seen that minimizing Bayes risk is same as minimizing the posterior risk. That means the risk with respect to posterior distribution of theta given x. And that is gives you a Bayes rule. Now then you did a result which said any Bayes rule is admissible, right? So let me so it says let delta pi be a, so there was a result which says that let delta pi be a Bayes rule with respect to a prior pi. If delta pi is unique Bayes rule, then delta pi is admissible. So that means any unique Bayes rule is always admissible. And so in general, then there was another part which says if for any decision rule delta, with R delta theta is a continuous function and pi b is greater, then delta pi is admissible. So that means under quite general conditions, any Bayes rule is admissible, right? But what we have obtained is many times you might have a decision rule which is not Bayes, but it is limit of Bayes. So the question is, if Bayes rule is admissible, can I say that estimators which are limit of Bayes are also admissible? So that is what the next result says. Let me see. So this is so any Bayes rule is always admissible. So then this is a result which says that even if you have a rule which is a limit of Bayes in the following sense, that means this limit goes to 0, then such a rule would be admissible. So let us try to see what this result says. This result says, suppose theta is a subset of Rk, that means you are dealing with a Euclidean space, is open. So your parameter space is open. And for any decision rule or for any estimator delta with a finite risk, R delta theta is a continuous function of theta. Now you know that this property is always satisfied for exponential families. So there is no problem if you are dealing with the exponential family, R delta theta would always be a continuous function of theta. So for example, if you are dealing with a normal distribution, there is no problem. This condition would always be satisfied. You are dealing with a binomial, you are dealing with a Poisson, and so on. So all this would always be satisfied. Then what I say is, suppose there exists a sequence of priors pi m, right? So prior distribution is fixed, but it says suppose you have a sequence of priors pi m. And these priors are such that they assign positive weight to every non-empty open set, right? They don't assign zero weight to any empty set, which is subset of theta. The Bayes rule risks are finite. So for each of them, the Bayes risk is finite. And then this limit goes to 0. Bayes risk of given estimator, which you want to test whether it is admissible or not, minus Bayes risk of Bayes estimator, because delta pi m is the Bayes respect to pi m. So it is a Bayes risk of the Bayes estimator. So note that normally this numerator would always be greater than or equal to 0, because R delta pi m is the Bayes risk of a Bayes estimator. So this would be the smallest among all estimators. So that means R delta not pi m would be greater than or equal to R delta pi m, because delta pi m is Bayes respect to pi. If this divided by pi m b is going to 0, what does that say? That means the Bayes risk of delta naught in certain sense is getting very close to the Bayes risk of Bayes estimator, which is delta pi m, right? Because this difference is going to 0. Of course, with a certain normalization, then any such estimator would be admissible. So that is what it is saying, that not only the unique Bayes estimator is admissible or Bayes estimator is admissible, limit of Bayes estimator, limit in the following sense, that means the difference between the risk of the given estimator and the Bayes risk divided by pi m b is 0 for any open set B, then I can say that delta naught is admissible. Right? So this is what it says. So what was your doubt now?
The doubt now clear, sir. I doubted regarding the theorem, which was not clear, but now it is clear.
Now it is clear because it says, what it says is you have to consider what it says. The first theorem which I had done was said that if you have a unique Bayes rule, it is admissible. Not only that, even if it has a Bayes rule and your risk function is finite, for any risk function finite, the corresponding decision rule is a continuous function of theta, which I said always happens in the exponential families. Then a Bayes rule is always admissible. So basically, last theorem essentially said that any Bayes rule is admissible. Now the question arises, sometimes I might not have a Bayes rule. For example, in the normal case, if you are dealing with a squared error loss function, X bar is not a Bayes rule. Why? Because it is unbiased. And you have seen that any estimator which is unbiased cannot be Bayes respect to a proper prior. But it can be, we have seen X bar can be a limit of a Bayes in this sense.
So can you please repeat that point?
Yeah.
Can you please repeat that point again?
So, so for example, let us look at if you're dealing with x1, x2, xn, IID normal theta 1, right? So X bar is the maximum likelihood estimator. It is also the uniformly minimum variance unbiased estimator. So suppose I have to see whether X bar is admissible or not, right? That is a question I want to check. So one thing is, first I try to check whether X bar can be admissible. If it is admissible and you're dealing with a normal distribution, which is exponential family, so it is admissible, exponential family, so it would be admissible. So the question is whether X bar is admissible with respect to any prior. But then we have done a result that under the square error loss function, if your estimator is base with respect to a prior, then the corresponding base risk has to be 0. Right? So that means if X bar is base with respect to corresponding prior, then the base risk has to be 0. But base risk of X bar is always 1 by n, because its risk is 1 by n constant. So its base risk could also be 1 by n, because average over the prior distribution. So X bar cannot be base with respect to any proper prior. So I cannot use that theorem. But this theorem fulfills that. He says that you don't need X bar to be base, even if it is a limit of base in the following sense. That means base risk of X bar with respect to any prior, which would be 1 upon n, because base risk of X bar is constant 1 upon n. So R delta naught pi m would be integral over respect to prior distribution of theta 1 by n, which would be 1 by n only. Minus base risk of a base estimator divided by pi mb as m goes to infinity. If this turns out to be 0, then X bar would be base. And one can show that this would happen. Okay. And that we have shown in one of those video lectures we have shown. If you want, I can go through that video lecture. So that is the thing, right? So is that okay now? The proof is straightforward, I guess. Is that okay?
Yes, the proof is okay.
Yeah. So any other doubt you have?
Sir, in the previous theorem, part C,
Right.
where capital theta belongs to R, K is open.
Yeah. Yeah.
So after when you are taking the risk of the base estimator and the difference of risk of base estimator and the yes sir.
Yeah.
Can you please explain the part of mirror image part when you are taking the mirror image of this difference
Inverse
of
image.
sorry, yeah, inverse image.
So you see, there is a result which you might have done in your analysis 1 course, that if f is a continuous function, right, then inverse image of any open set is open, right? That is the result which is known. So if f is a continuous function from R to R, then inverse image of any open set has to be open. This is a standard result in the analysis, right, in the calculus. That is what I have done. So I consider A to be correction of all those thetas, so that R delta pi theta minus R delta star theta is greater than epsilon by 2. So what is this? This is inverse image of the set epsilon by 2 to infinity, right? Open set epsilon by 2 to infinity. Is that okay? Because this is, I'm looking at what are those points in the domain such that R delta pi theta minus R delta star theta is greater than epsilon by 2. So let me call this function, this difference function as f theta or h theta, right? Let me call this function as h theta. So I'm looking at collection of all those thetas such that h theta is greater than epsilon by 2, which is same as h inverse of epsilon by 2 to infinity. So that means h inverse of the set epsilon by 2 to infinity, and epsilon by 2 open because you have a greater than over here.
Yes.
H is continuous because R delta pi theta is continuous, R delta star theta is continuous, so their difference is continuous. So H is continuous. And epsilon by 2 to infinity is an open set. So H inverse epsilon by 2 to infinity would be an open set. That is what it says. It says A is an non-empty open set. Is that okay?
Yes, sir.
Inverse image of a continuous function is an, for a continuous function, inverse image of an open set is always open. This is the result you use.
Okay. Thank you, sir.
Okay. Yes, any other?
Sir?
Yeah.
Sir, why the base risk of base estimator is minimum among all the estimators?
Because that is a definition of a base estimator, right? Base estimator is the one which minimizes the base risk. That is a definition, no? Let's look at the way we have defined the Bayes estimator. So you see, what you have is, you have a prior distribution pi, right? Which is nothing but a probability distribution over theta, right? Which is a probability distribution for the parameter you are considering. Now, normally what I have is, I have a R delta F or R delta theta. Is that okay? Now, R delta theta is a risk which depends on theta. But now theta itself is a random variable. So I take the average of the risk R delta theta. That is what the Bayes risk is. So Bayes risk of an estimated delta is nothing but its average risk with respect to the given prior distribution for the parameter, right? This is what the Bayes risk is. Now, so each estimator will have a Bayes risk. And I'm saying a Bayes rule or Bayes estimator is nothing but which minimizes the Bayes risk. That is what it says. It should be R actually. It should be small r. Capital R over here, it should be small r delta. So that means for the Bayes rule, R delta pi is minimum among the Bayes risk of all the estimators. Infimum delta belonging to delta, R delta. Is that okay?
Okay, sir.
And then we have seen that to find a Bayes estimator, you can only take the Bayes action. Bayes action is nothing but you just
Bayes
minimize the
estimate.
posterior risk. So you just look at the distribution of theta given x equal to x and see what A minimizes that. That would be the Bayes estimate. Is that okay?
Yes, sir.
Yeah. Any other doubts anybody has? So somebody who asked this question, this theorem, limit of Bayes. In one of those lectures, I have shown that X bar is admissible. And how I have shown X bar is admissible? To show that, as I said, to show that X bar is admissible, you try to show that under the square error loss function I'm talking about. Either so it is Bayes, which is not happening because it cannot be based under square error loss function, or so that it is a limit of Bayes in this sense. So that means first what I need to do is to apply this result, I need to have a sequence of priors. In one of the earlier things, we have seen that X bar is generalized Bayes. It is not Bayes, but it is a generalized Bayes. If you look at over here, to estimate theta under the square error loss function, I've considered a prior which is a uniform prior on whole of R. And then I try to minimize this. And I see that minimizing thing is X bar. So I say that X bar, although is not Bayes, it is generalized Bayes. It is a generalized Bayes, that means it is a Bayes when there is no prior information. Because pi theta is a uniform prior, I'm saying, on the whole R, right? If you take pi theta to be uniform prior on the whole R, then X bar turns out to be Bayes. But uniform distribution on whole R is an approximation of a prior which says that there is no prior. So it can be treated as an approximation of even a normal prior when variance is going to infinity. Is that okay? Because if I take a normal prior and take variance going to infinity, that may look like a non-informative prior. So what I do is, in this problem, when I apply this result, I take my pi m to be normal 0 m. Mean doesn't matter, so normal 0 m I take, right? Pi m to be a prior distribution. So the prior distribution of theta to be I take as normal with mean 0 and variance m. M is equal to 1, 2, and so on. Because as m goes to infinity, variance would go to infinity, so that prior would behave like a uniform prior, right? So I take m to be, theta to be normal 0 m. Now, if you take theta to be normal 0 m, what is a Bayes estimator? Does anyone remember what is a Bayes estimator with respect to prior normal 0 m? You can see the video lectures. I said it would be some type of so you have a two kind of a means. One is a mean from the prior distribution, one mean from the data. So it would be kind of a convex combination of the two. and convex combination depends on the weight of the variances. So x bar, what is the variance of x bar? 1 by n, right? So it will be n x bar plus variance of prior distribution is 0. And then weight is variances, so 1 upon n plus m. So you can derive that, right? That I have derived in lecture notes. So I derive the Bayes estimator. I can find out its Bayes risk, R delta pi m pi m. R delta naught pi m I know because x bar has a risk 1 by n, so R delta naught pi m would be 1 upon n. So it would be 1 upon n minus the risk of the Bayes estimator, which is straightforward to find. And then try to show that this minus this divided by pi m of any open set, which could be of the type A to B, is 0. Right? That is what I try to show. And that is what I have shown in the lecture notes, video lecture, and which proves that x bar is admissible. Similar thing you can do under the absolute error loss also. Is that okay? Yeah, any doubt you have or any? You want me to repeat that lecture where I am showing that x bar is admissible? Yeah? Have you seen that video where I have shown that x bar is admissible in the normal case?
Yes, sir.
You have seen that, right? So it is exactly this result.
Yes, sir. Sir, can you explain the definition where you define a Bayes estimator is unique? Or when do we say that Bayes estimator is unique? That definition.
That means wherever you are minimizing that posterior distribution, that is a unique minimizer. That is what it says. That means if you have any other minimizer, then the two should be same with probability 1. That is what it says.
Oh, okay, sir.
Right? It is a unique minimizer. That is what it means. That means you can have another minimizer, but the probability that they would be different is 0. Or in other words, probability that they would be the same is 1. For example, you see, I mean to say, if x bar minimizes the posterior risk, what I do is I change x bar at one point. So I define new estimator, delta star, which is same as x bar, if x bar is different from 0, and 2 if x bar is 0. Right?
Yes,
okay?
sir.
Now this will also minimize that, but then this estimator is same as x bar is probability 1, because the point where they differ is only x bar is equal to 0. And probability x bar 0 is equal to 0 is 0.
Yes, sir.
So what it means is, if Bayes estimator is essentially unique, that means the probability that they are different is 0. Then a Bayes estimator would always be admissible. For example, under the square error loss function, when we minimize the posterior risk, square error loss function is a strictly convex function. So all such minimizers are unique minimizers. Is that okay? And if
Yes,
they are
sir.
unique minimizers, then that means all they are admissible. Is that okay?
Yes, sir. It's okay now.
Yes, any other doubt? So this is the result which says that delta naught be a Bayes estimator of theta with respect to prior under the square error loss function. If delta naught is unbiased, then R delta naught pi has to be 0. Right? So for example, if you have to show that in the normal case x bar is not Bayes, how do you show? I know that x bar is unbiased. Right? So if under a square error loss function it is Bayes with respect to some prior, then the Bayes risk has to be 0. Because x bar is unbiased. So if x bar is unbiased and also Bayes, then its Bayes risk has to be 0. But what is the risk of x bar? It is the variance of x bar, expect to x bar minus theta whole square, 1 by n, which does not depend on theta. So what would be its Bayes risk? Average of 1 over upon n with respect to prior distribution of theta. Whatever prior distribution of theta would be, it will be a probability distribution. So average over 1 by n would be 1 by n only. So the base risk of X bar is 1 by n, whereas if it was a base, it should have been 0. So under the square error loss function, in the normal case, X bar cannot be base. And that is what one can show using this result. That is what I have shown over here. Right? Yeah, so that result which I was talking about is over here. Let x1, x2, xm be a normal random sample from normal mu sigma square, where mu is unknown and sigma is known. Under the square error loss function, so that X bar is an admissible estimator for estimating mu. So suddenly, if it is a square error loss function. So if it was base, it would have been a unique minimizer. So X bar would have been admissible. But we know that X bar cannot be base because of the last result which we discussed. So what I try to do is we try to show that it is admissible. We try to show that it is a limit of base. So for that, I consider a sequence of prior pi m, which is normal 0 sigma m square. In fact, I could have chosen normal 0 m because finally I have to choose, because I know that X bar is not a base, but it is generalized base. Generalized base with respect to uniform prior. Uniform prior means that means no information, which is equivalent to saying in certain sense that variance goes to infinity. So that means I consider a prior pi m, which is normal 0 sigma m square, and then I take sigma m square going to infinity. Right? I can always take because it is a sequence of priors. Now, certainly this prior satisfies the condition of last theorem because pi m of any open set is positive, right? Because it is a continuous distribution. So if we integrate A to B of a normal density, it will always be positive for any A and B. So if it is a pi of any open interval is positive, pi of any open set will be positive because open sets in real line are nothing but union of open intervals. So if open interval itself is positive, union of open intervals pi would always be positive. So this is what it happens. Now I have to find a base estimator with respect to prior pi m. To find a base estimator with respect to proper prior pi m, I need to find out what is a posterior distribution. So what is a posterior distribution? S given x at the point theta given x. So it is a conditional distribution of theta given x. And conditional distribution is proportional to the joint distribution, right? You know. Because it is a joint divided by marginal, but marginal of x here is a constant because here theta given x I am talking about. So the conditional distribution is always proportional to joint. And what is a joint? Distribution of x given theta. This is what usual classical distribution of x given theta. Then the prior distribution of theta. What is the distribution of x given theta? I had assumed that x1, x2, xn are ID normal mu1. This should have been mu, doesn't matter. So 1 by 2 pi sigma square to power n by 2 e to power minus 1 by 2 sigma square summation I is equal to 1 to n xi minus mu whole square. So that is f theta x. What is the prior distribution of s? Normal 0 sigma m square. So which is 1 upon sigma m root 2 pi e to power minus 1 by 2 sigma square. I make it a perfect square and do it. So it turns out to be e to power minus half mu square upon sigma m square plus n by sigma square. I can take this side outside and then I can make it a perfect square. So it will become mu minus 2 times this divided by this whole square. So it looks like it is a normal density. And normal, what would be the mean? Because this would make it a perfect square. This is a cross product term. So 2 mu. So it would be nx bar by sigma square divided by, because this I'll have to take out to make it a perfect square, mu minus something. So nx bar by sigma square divided by 1 upon sigma m square plus n upon sigma square. And what is the variance? Variance is, because this goes outside, so it is a 1 upon variance. So this is 1 upon sigma m square plus n by sigma square to power minus half. Under the square error loss function, what is a base estimator? Posterior mean. And posterior mean is nothing but nx bar by sigma square divided by this. So I write down like this. So this is the estimator, which I can write down like this. So this is a base estimator. Now you can see that as sigma m square goes to infinity, this quantity goes to 0 and it becomes x bar. So which is coincides with our intuition that we had seen that it is generalized base. Generalized base amounts to saying that variance is going to infinity. So I consider any prior where variance is going to infinity. For normal, the conjugate prior is normal only because to deal with normal would be easier. I consider a normal conjugate prior, but I made variance going to infinity. So this is the estimator. So now the only thing I have to show is that R delta not pi m minus R delta pi m divided by pi m b goes to 0. So that means I first need to find out what is the R delta pi m x. So base risk of R delta pi m, which is expected value with respect to pi m, and the risk of x bar. This is a usual risk. What is the usual risk? Anyone? Usual risk is same as, it is not unbiased, so it is same as variance of this plus bias square. Variance of this is nothing but variance of x bar divided by this square. So variance of x bar is nothing but sigma square by n divided by sigma square by n sigma m square plus 1 whole square, plus bias is nothing but mu upon sigma square upon n sigma m square plus 1 minus mu whole square. I simplify it this. This does not depend on mu, because so the prior distribution would be constant. So risk would be constant. It is sigma square by n upon sigma square m. So this expectation doesn't play any role, right? Because this expectation involves the prior distribution to the parameter, which is mu, which is this. But this itself does not. No, it depends on mu. It is a mu coming over here, right? There is no mu over here. Mu is coming over here. Mu comes outside, that becomes expected of mu square. Under the prior pi m, mu is normal 0 sigma m square. So that means expected value of mu square would be sigma m square. And that is how this sigma m square is coming. This goes outside and this becomes common. This is what it is. So this is what R delta pi m becomes. And R pi m delta naught I know is sigma square by n, right? Because its risk itself is sigma square by n. So when I take the average, that remains sigma square by n. So I have to see whether R pi m delta naught minus R pi m delta pi m by pi m AB for any open set goes to 0 or not. So this turns out to be sigma square by n. This we have already calculated over here, sigma square by n this by phi of, what is pi m AB? Pi m was normal 0 sigma m. So it can be written as phi b upon am minus phi a upon a. So I do that. Sigma square and by gets cancelled, so it becomes 1 upon sigma m square plus sigma m square quantity list. Now what I'm saying is I choose sequence of priors such that sigma m goes to infinity. For example, I could have chosen sigma m to be root m or sigma m square to be m. Then what happens to phi b upon am minus phi of am? This you will see that it goes to some constant, right? This goes to infinity, so everything goes to 0. So this is what it is going to 0. Is that okay? Is that clear?
Yes, sir. Yeah.
Okay. Actually, if you look at this quantity, phi of b of sigma m minus phi of a upon sigma m, you write down this in terms of a PDF. This is nothing but a to b 1 upon sigma m root 2 pi e to power minus x square upon twice sigma square, twice sigma m square. That 1 upon sigma m root 2 pi, I take it over here. Then since it is a sigma m square over here, even if I take a sigma m over here, that quantity will go to infinity, right? Because if I take sigma m over here, so it will be sigma m plus sigma square by n sigma m. So this itself would go to infinity. Then what is remaining over there is integral minus infinity to infinity e to power minus x square upon twice sigma m dx. E to power minus x square by twice sigma m as sigma m goes to infinity goes to 1. So you are left with a phi m of integral a to b dx, which is very good b minus a. So this everything goes to 0. So that is what it is. Yes, any other doubt you have? So this shows that x bar is admissible. So let me stop here. Yeah, any other doubt anybody has? Yeah. Yes, any doubt? So everything is cool, right? Very easy, everything, right?
Sir, we haven't watched all the videos of this lecture yet.
I have done.
Sir, no, sir. We did not watch
Okay, you
all
have
the
not gone
videos.
through it.
Yes, yes, sir.
Then we can have another discussion hour if you want. Just send me an email if you want. We can have another one on Sunday. If it, right, so you can go through it and try to this. We'll have a one tutorial session on Friday. Now, if you want, as I said, now this time I might not have the solutions available with me. But if you tell me in advance that these are the problems which you are having difficulty, then I can write down a solution of mine, scan it, and then I can show it over here, right? And then I can share with you. Otherwise, writing down all the solutions is taking a lot of my time because I'm spending a lot of time in making these videos, making these lecture notes, modifying it. I'm not getting enough time to write down each and every solution very meticulously. I did it for first 3 assignments. I can still do if you tell me in advance. So for example, Friday, if I have a tutorial, if you tell me that, okay, sir, these are the problems, if you just let me, or even after Friday, if you tell me that these are the problems, if you can share the solution, it will be fine. But it should not happen that you share different problems and each one tells one problem and then finally it turns out to be the whole assignment. Is that okay? So just genuine ones and try to discuss something between you yourself also. Some of the problems are straightforward, which may not require any assistance. Some of them may be difficult and may require some additional further reading. So just let me know if you want. I'll certainly write down. But certainly writing down all the solutions, I think, because it's becoming too much for me.
Sir, what will be the mid-sem syllabus?
Same assignment 4 up to assignment.
Okay.
In fact, whatever, yeah, last videos, whatever videos we have uploaded already. Is that okay?
So up to week 6?
Yeah, to week 6. Yeah.
Okay, sir.
Okay, sir.
So what will be the pattern of the exam?
That is a difficult question. How can I tell you pattern?
In
What do you mean pattern?
like we had for quiz, will it be similar to that? Or?
It will be similar kind of a thing. So there'll be, what I will do is, this is a 2-hour question, 2 hours, so I'll make it 2 parts, right? Quiz of how many parts did we have?
3 parts.
3 parts, sir.
One part is
2
one.
out of 3.
So 2 out of 3. So here I'll make only 2 parts. Both would be compulsory. So 1 hour, roughly 50 minutes each, right? Or 1 hour each. And then, so essentially there are 4 topics, right? One is a location invariant estimation. One is a scale invariant estimation. Then affine, and then base and minimax, right? So what I will do is I might have 2 questions each from base and minimax, or in all I might have 3 questions from affine and base, right? And 1 question from location and scale. Is that okay? Because location and scale is already covered in the midsem part, so there would be lesser weightage here because that's already covered. So yeah, I think let us fix that. So 4 questions, 1 from the location and scale part, and 3 questions from base, minimax, and when I say 3 questions, these questions might have a part, right? A question might have 2 parts, right? Is that okay?
Yes, sir.
You have other exams as well?
Yes, sir.
What are the other exams you will have during the midsem?
We have stochastic time series. All
But they all are taking MCQ, no?
No, sir. That's not the case. Only time series is MCQ and others has not been decided by the teacher.
But how did they take quiz?
Quiz was all MCQs, but midsem may be different.
Yeah. But midsem is not decided. So our mine would be exactly on the same lines, right? So how are you finding MC? You're finding MCQ better or these descriptive ones better?
No, sir. Descriptive ones are better because for MCQ we have to do every week exam.
But MCQ cheating may be easier, right? You can quickly pass on. So MCQ, how many sets they make?
Sir,
So
there are random questions
randomized
and also
questions.
teacher gave us very less time to solve it.
Yes, sir.
2 minutes for one question.
How many questions are there in a quiz?
Around 10.
So 10, but randomized, their order may be randomized, right?
No, sir. There
No,
are
sir.
also
Questions
different
are
questions
different.
for different students.
Different questions for different students.
Yes, sir.
Uh,
So like we need to code and the values are different for each question.
that is okay. That is okay. Which course is this?
Simulation and data analysis.
Who is taking this course?
Dutika ma'am.
Achha, so those parameters see changes, right? And then, yeah, okay. Good. So so which course you are struggling the most?
Inference too, sir.
Friends too, sir.
Whereas 2 you are struggling the most. Right. Slightly abstract course, but then yeah, means you have to do assignment problem. There is no escape. You have to have some practice. Concepts are not that difficult. It's only implementing them. Sometimes in some typical problems, it may be difficult. Okay, any other doubt you have? Anything you can ask from? Yes, you can ask anything. You don't want to ask? You haven't gone through the lectures, so. But are these lectures clear? Which you, when you watch, are you able to follow them?
Yes, sir.
Yes, sir.
Yes, sir.
These notes also may be useful, right?
Yes, sir.
Yeah, you have to spend time. Means I understand you all must be your priorities this semester must be your placement, and that's a reason why possibly you may be feeling overburdened.
Yes, sir.
But that is what the education is. Education is not what you learn in this inference too, right? Few theorems and corollary. The education is you have to manage all this. You have to manage Professor Misra, you have to manage Kritika, you have to manage. This is what is going to be with you throughout your life. And there is no escape. You have to go through this process. And how are the placement scenario this time? It looks like better. So
So there is a problem.
yeah.
So there is a problem like some profiles, some companies offer a profile of data scientist, and they are not opening for us.
They may be taking more from computer science, right?
Yes, sir.
Yes.
They are closed for us.
Yeah, that's a problem. That's a typical bias many companies have because and
Sir, even one profile is open for MSc Mathematics and not open for us.
oh, the one is profile for so they may, which company is this?
Alfonso,
Achha. And what is the nature of a job?
data scientist.
Achha.
That is not open for MSc Mathematics. That is open for MSBA student, I think.
No, that is open
Mathematics
for
and
mathematics.
computing.
MSc Mathematics also.
That's a
Mathematics
no
and computing.
bias personally. But what is a data science?
Statistics.
Analysis of data.
Huh?
Science of data.
Has anybody tried to explain you what is a data science?
Analyze the data and obtain some insight about the data.
That is a data analysis. The data science in the modern time, what it is being referred to. To whom you will call a data scientist?
Who can analyze the data and then find the insights of the data and
That any
implement it in
any statistician can do.
Yes, sir.
So all statisticians are data scientists by your definition.
No, sir.
So it's a confusing. I have never been understood, and no one has been able to define data scientist in a very. The closest definition which I could locate is the one which I read somewhere in the web. A data scientist is someone who knows less statistics than a statistician, but knows more programming than a statistician, right? So that is what the data scientist is. So a computer scientist can be called as a data scientist because he knows less statistics than a statistician, but more programming than, or more coding, or better, he's well equipped with doing good to coding than compared to statistician, and vice versa. So these are, I find, very confusing terms because it's one can give vague definitions in the sense that certainly data analysis techniques are covered under classical statistics. Now the issue is you have now data. You see, early days, why statistics was so important was data was limited. So you need to have a tools to squeeze the data, right? Get everything out of the data. But now say that, look, there is no problem of a data. There is no need to squeeze it. You will have enough data. Whatever you want, you have. So I can give you the essentially whole population. Right. So, for example, if you want the shopping interests of IIT Kanpur students, I can give you whole data. Not only this, I can give the shopping inclinations of not only ITK students, their whole family, their ancestors, and not ancestors, but at least immediate family members, right? With the help of Google, now everything is available. So data is not a problem. So that means now, so big data itself becomes a problem. Now the issue becomes how to, now you see too much data is also a problem because
Curves of dimensionality. Curves of dimensionality.
Yeah, so that is where the computer science comes in. So what you say is, look, sometimes data may not be very structured. So somehow can we develop systems so that system itself starts playing the role of a statistician? And that is where this deep learning and machine learning and all those fields come in. So sounds very interesting. So, but incidentally, it's very difficult to find places where good data science programs are there, because these would be one. So, and that's a reason what statisticians fear these days. With the advent of this data science, the statistics field may just vanish in its present form. It may be taken over by computer scientists, and they may give a new name to it, which is data science. So that's a challenge. So statisticians also have to change, right? The nature of statistics has to change. Otherwise, I think it is one of the discipline which I don't see a very good future unless the nature of the field changes. Right? They become more. They also learn. They start doing a lot of computer science also. Okay. Okay. I think we are done. So try to go through these notes. If you need, we can meet once again. But what I would suggest is, at least for the Friday tutorial, try to do problems. If you feel that there is some problem I should specifically discuss, just let me know one day before, by Thursday afternoon, so that I can write it down and then I can share the screen. I can discuss all the problems, but discussing with screen share always becomes easier if it is a difficult problem. Easier problem we can always discuss, and I can explain what is the concept involved. Is that okay? So we'll meet on Friday. If the need be, we'll meet on Sunday as well. Is that okay? Okay.
Okay, sir. Okay.
Yes, sir.
Thank you, sir.
Thank you,
Thank
sir.
you, sir.